Okay, so before the break, we were talking about algorithms, and we kind of informally defined an algorithm as a series of steps that are being performed, and likened it to things like long division. Could be an elementary algorithm. We were talking about this idea of the car, the self-driving car, trying to stay between the lanes or stay on target in a particular line and kind of self-correcting itself. Okay, so maybe it's going off in this direction. Oops, got to correct, go this way, and try to stay on that straight line. We also talked about Gaussian elimination. Now, the Gaussian elimination algorithm was a way to find the inverse of a matrix. So what kind of joins this to the Gaussian elimination is simply the idea of an algorithm. Okay, so be sure not to think that, well, this is equivalent to Gaussian elimination, because it isn't. The idea of an algorithm is everywhere. And even when you think of algorithms, you think of, say, what you do when you make coffee in the morning, right? You like pour the water, put the filter in, kind of a step-by-step process. And if the coffee doesn't work out after the taste test, then you make another batch. So you get to step 5 of the algorithm, and that's the taste test. You taste the coffee, say this didn't work, something went wrong, repeat step 1, or go to step 2 again and repeat through step 3, step 4, etc. You think of that in terms of like an algorithmic thinking. And when we talk about algorithms later in the course, we're generally referring to that kind of like instruction idea of today. It's kind of like what we want the computer to do. And the computer, when we're operating our computers, they're performing many different algorithms to complete different functions. I mean, even when I draw the pen like this, there's some kind of a computation that's being done to get that done. And it's all based on all those ideas of kind of instructions. Okay, so, and before the break, so we surveyed some of the elements of matrices. We talked about inverses, talked about addition of matrices, multiplication of matrices, excuse me. And now let's continue with the topic of determinants. Well, determinants are actually pretty important, and we'll look at a kind of an applied example here. But when we talk about the determinant, we talk about a number, okay? So it's associated with a scalar, which is a number called the determinant, and it's often written DETA. Sometimes it's written like this, depends on the book. Okay, mathematical and statistical notation is not standardized. Very important, it's not standardized across sources, which makes life miserable, right? Because you see this in one book or one source, and you have to figure, what are they talking about? Is that the determinant? Or is it the absolute value of a number? Or what's going on? And you have to kind of look in the book to see how exactly they're using that particular notation. And same thing over here. Okay, now that's pretty straightforward, but in some cases it won't be. Now, what's a determinant? Well, here it is for a 3x3 matrix. There's a computation for the number, but honestly, the easiest way to learn a determinant is to focus on the 2x2. Don't even go by the 3x3 because the intuition isn't as strong. So I'm going to draw a 2x2 matrix here, A, B, C, and D. Okay, this is what the determinant is: A times D minus B times C. A times D minus B times C. That's the determinant for a 2x2. 2 columns, 2 rows, there's your determinant. And that's the same thing that's being outlined over here. The difference is I went AD, whereas in Fox's notation, it's A11, A22, because this is in row 1, column 1, and A22 would be over here. So that's those first 2 numbers, minus A12, A21 is going to be those 2. So that's going to give you a number. Let's say is equal to 5. Now, why is that number important? Well, let's put a real substantive application on this. Now, when I say substantive in this sense, we're kind of in the abstract here, because what I'm saying is you've got this artificial thing called a determinant. It's very abstract, yet I'm going to make it concrete by coming up with a theoretical example of how it's used in multivariate. So we're still not at the level where we're actually talking about real data. We're not at the level yet where we're talking about real things. We're kind of going from one level of abstraction to something a little bit less abstract. Once we get into the statistical learning book in a couple weeks, then we're going to be getting into, talking about like real data and things like that. So when we talk about the determinant, here's how you can think of it in terms of an application. Remember the variance covariance matrix. There's a variance, there's a variance, there's a cov, and there's a cov. Those two covariances, by the way, are going to be exactly the same, because you have x1, you have x2, you have x1, and you have x2. That's the variance of x1, that's the variance of x2, that's the covariance of x1 and x2, covariance of x1 and x2. So these are exactly the same, those two covariances. So, you can pick some variables here if you want. Maybe that's age, and then we have, say, like weight or something like that. Well, there's probably a covariance between age and weight right over here. There's also a covariance due to age, and there's a covariance due to weight, or a variance due to age and a variance due to weight. That's in this main diagonal. So when would we want to compute the determinant? Well, imagine if you have this covariance matrix. That's a covariance matrix. Let's compute a determinant on it. Well, what would the computation of a 2 by 2 matrix computing the determinant on this look like? Well, let's go by our formula over here. What does the formula say? Formula says take this variance, multiply it by this one. A11, A22, right? These are just element numbers. They happen to be variances in this case. So take this one times this one. Then subtract out this covariance times this covariance. So let's think about this. Why might that be important? Kind of previewing where we're going with this. Well, we have two variances. That's going to give us a number. Let's say when we multiply those two variances, it gives us, say, 10. If we have 0 covariances, so I'm going to pretend like this is 0 for just a second, and therefore this is 0, what are we subtracting out? We're subtracting 0. Therefore, this determinant is equal to 10, right? That makes sense. So if this is 0 and this is 0, we're going 10 minus 0 is equal to 10. However, what if this number was not equal to 0 and this number not equal to 0? So let's say that this is like 2 and therefore this is 2. Well then, what are we subtracting out? We're subtracting the product here of 4. Therefore, this number, 10 minus 4, is equal to now 6. Now, there's a reason why I wanted to use this example of the covariance matrix to illustrate the determinant, because we can think of this in terms of a generalized variance for this matrix. Okay, this idea of a generalized variance. Now, look at this particular situation again. In the first case, we're subtracting out 0 covariability between variables. Therefore, all we're accounting for is the variance because we have 0 covariability. But in the second case, this number dropped down to 6 because we subtracted out the 4, right? Because we subtract out the 4, because in this particular case, that example, we had 2 and 2. So here's the idea. Can you kind of see where this is going? What is that determinant actually communicating in this matrix? What it's saying is that if you have covariability between variables, you cannot double dip, right? That's kind of like what it's saying. It's saying if you have covariability, you better subtract that out. So let me just put that one down here just so it's a little bit clearer. You better subtract that information out for the overall variance of the matrix. If you don't have any covariability, you don't have to subtract anything out. Well, you're subtracting something out, but it's 0. So you end up with just 10. So in a sense, this idea of covariance here between x2 and x1, you can think of that in terms of getting rid of that overlap, kind of like the Venn diagrams, right? You've got some overlap, you're subtracting out the overlap so you don't double dip, right? You don't pretend like there's more going on in your matrix than there isn't. So, someone, is walking on the street and asks you how much variability you have in your matrix. In this case, you say, hey, I've got 10. But in this case, you say you only have 6, even though the product of variances in each case is equal to 10. Why? Because you're honest, right? You don't want to double dip. You say, well, you got to subtract out the commonality because there's some shared variance. So it's actually down to 6 over here. Powerful, powerful way of understanding how determinants are going to be used in multivariate analysis. Okay, so you remember that when we get to some further stuff. Here we've got some properties of matrices of determinants, not important. That's all we need to really know here. Kronecker product, you skip all this. Certain product that's used in linear algebra. Very, very few areas in multivariate analysis is it seen, so you don't have to worry about it. You have to worry about this though, basic vector geometry. So we talked about vectors already. There's a vector. Now the vector is usually represented by like the little x. Sometimes a vector will also be like this with a little arrow on it, magnitude and direction, so that'll be the symbolism for it. Talking about matrices, by the way, you have a big X. So little x is for the vectors. They're the elements of your vector, and that's indicating that idea of transpose. Directed line segment extending from the origin of an n-dimensional Cartesian coordinate space. Remember what a Cartesian coordinate space is, right? So we have one dimension, x1, x2. That's how we do scatter plots. One dimension here, one dimension here. There's 2 dimensions there, but we don't need to stop at 2. And this is a multiple or simple linear regression. You're in the 2 dimensions. But when you get to multivariate analysis, which is what we're in now, well, the sky is the limit, right? We don't have to stop with 2 dimensions. Hey, we can have a 3rd dimension. Why stop with 3? We can have 4. I don't know where to draw it on the page because you can't visualize it, but you get the idea. 4, 5, 6, 7, etc. n-dimensional. So how many dimensions can we have? Well, in some of these problems they're doing with like principal components and dimension reduction, you could have thousands of dimensions. So imagine we did this. Imagine I gave you a whole bunch of variables. Okay, a whole bunch of variables. And each of these variables corresponds to a single dimension. Well, let's say I have 1,000 dimensions. One central question of multivariate analysis is whether we need those 1,000 dimensions to account for the information in all of those variables. Do we really need 1,000 variables to get across the information that we want to get across? Maybe not. Maybe we could do something that's going to be called dimension reduction. Okay. What if we can reduce the number of dimensions from 1,000 to 5? So instead of needing 1 dimension, 2 dimension, 3 dimension, 4, 5, all the way up to 1,000. Imagine visualizing the 1,000 here. It's impossible. But technically it can be done. We just can't see it. But imagine taking those 1,000 dimensions and reducing it down to 5. Well, if I told you that, I would say, I've got 1,000 dimensions of which I've recorded data, and I reduced it down to 5 by some procedure. Well, what would you say? You may say, well, did you lose any information in doing so? Is all the information still accounted for? Surely. I mean, what's the sacrifice here of going from 1,000 to 5? Maybe you lost information. And we will lose information, but it's how much? So if this is, say, 100% of the information, and I get it down to 5 in terms of dimensions, what if I told you this? What if I told you that I was able to retain 90% of the information from this original 100% down to 5 dimensions? I was able to retain 90%. You may think, wow, that's great, because you can reduce the dimensionality while maintaining most of the original information. Dimension reduction, that's where we're headed with principal components, and to some extent, though not the same, factor analysis. Central problem of multivariate analysis. Realize too that when we talk about all these dimensions, I haven't talked about a dependent variable, I haven't talked about an independent variable like we'd have in ANOVA or regression. We just have a whole bunch of variables and we're trying to get them down to fewer dimensions. You can also liken that to the idea of with a matrix. So let's say I have x1, x2, x3, x4, all the way to xn. Well, I've got, say, several data points for each variable. And what if I told you that I can actually account for the information in this matrix by just 2 dimensions? That's the same idea. Reduce this matrix of 1,000 columns by 1,000 rows to something much less. Now, I'm going to give you the hint here. It's not going to be these original variables. It's not like I'm going to say, hey, I have like 1,000 variables, but I'm just going to keep these 2 variables. That's not going to work. What we're going to have to do is we're going to have to transform this matrix into something else. We're not just going to keep a few of the variables. We're going to have to make a transformation on the matrix so that we are kind of transforming the dimensionality into 5 dimensions instead of 1,000. And that's what principal components analysis is going to be about, because we're going to learn how that's actually done and how we can make some meaning out of those 5 dimensions. So all that started here with the idea of the vector. And here are some vectors in higher dimensional space. So there's x1, x2. Here there's only 2. So, this is like x1 equals 1, x2 equals 2. They're different positions right here. 2 dimensions. Well, here's 3, 1. There's x3, there's x2. And we have those 3 coordinates. So, that particular point, again, you get into 3 dimensions, it's really hard to visualize. It's hard. This, no problem. This is the multivariate problem. We get into higher dimensions. Here there's 3, but we can go to xn. We don't have to stop with 3. We can go higher. But we get the idea. We get the idea of how these vectors play out in space. And again, whether you wish to kind of visualize those vectors in space or just think of them in terms of lists of numbers, that'll change depending on what we're doing. Here's the addition of vectors. Not interesting. You can read it. There's a subtraction, not particularly useful. The length of a vector is kind of important, but that's only going to come into play when we talk about different procedures later on. The length is denoted like this, and it's the square root of its sum of squared coordinates. Sum of squares, take the square root. Now, if you look at this, does that ring a bell? That might ring a bell a little bit. What gives it away is the square root sign. You say, wait a minute, we've kind of done something like this before, haven't we? Because we have a sum of what? What are these? Those are squares. Well, what have we summed the squares of in so-called univariate statistics, which is the statistics before multivariate? Like the one, when we use one dependent variable and we only have like simple linear regression, univariate and bivariate. So we've done this before. Now we took the square root. The standard deviation can be likened to this concept of length, depending on what these squared units are. In the case of the standard deviation, these are the deviation values, or just d sub I. Okay, so there's something where you say, wow, the length of the vector, we actually kind of know a little bit about that because we've talked about the standard deviation and computed standard deviation. So right, we can liken that to a previous statistical concept, not one that we're going to see, but one that we've already seen, and say, see, we've actually been computing something like the length. We just didn't call it that. We had no reason to call it that. Product of a scalar and a vector is the following. So AX, where A is a scalar and X is the vector. And what this does is this lengthens or shortens the particular vector. So here's some examples of length, and those are in 2 dimensions and 3 dimensions. So this is exactly how we compute the length here. Sum those squares, take the square root, and this is the idea of the scalar idea. So you got a vector, you have a scalar. Well, the scalar here is 1.5, and the vector is x. So watch how this works in the vector space here. Is you have 3, 2, which is our vector. And what we're doing to this vector is we're applying a scalar. The 1.5 is the scalar. So what effect did the application of the scalar have on the vector? What did it do? Well, there's the original vector, because it's at 3, 2. There's 3. There's 2. What effect did it have? It lengthened it, right? We applied the scalar and it lengthened the vector to these new coordinates for the vector. So we're multiplying the vector by a scalar. So think of the scalar as, I mean, this is going to sound silly, but it's scaling the vector, right? I know that doesn't help, but if you kind of get the idea of, hey, scale that vector, scale it. How long should it be? How short should it be? Take the vector and change it by a scalar factor. That's exactly what's going on here. We could also go in the opposite direction too, negative. So instead of 3, 2, what did we scale this by? -1. We scaled the vector by -1 and we got our new coordinates going this way. So we can go in either direction with the scalar. Now, figure, my goodness, like, why is this important? Well, it's important because we're soon going to see this equation. And this is going to be for computing eigenvalues and eigenvectors, where this is going to be a vector. That's a vector. That's a matrix. And this is going to be a scalar. That's going to be a scalar, and it's going to be called an eigenvalue. The eigenvalue is going to scale the vector. Very similar to this right here. Okay, so we're going to return to that in a second, but this is kind of what we're dealing with. Figure, well, where are these going to come up? They're going to come up in principal components analysis, where we try to get the vectors that explain most of the variability. A little bit of stuff there you can look at if you want. Vector spaces and subspaces. We talk about a vector space of dimension n. This is the infinite set of all vectors. Okay, this is infinite set of all particular vectors. Now the coordinates may be any real numbers. Okay, so the vector space of dimension 1 is the real line. So the line is actually a vector space of dimension 1. Then you have the vector space of dimension 2 is the plane, and so on. So again, you can work, the mathematician at least, they work in like multiple dimensions. There's no, we're in the abstract for a second. I promise you we're going to be getting concrete soon. But we're in the abstract where, hey, anything goes that we can imagine in terms of the number of dimensions. There's 2, there's 3, there's 4, etc. And you've got this whole set of vectors in that space, which is comprising the vector space. Now, in that complete vector space, you can have a subspace. Okay, you can have a subspace. Think of it kind of like a subset, right? Like a subset, but it's a subspace of the more higher dimensional vector space. That subspace is generated by a set of particular vectors. Okay? It's generated by a particular set of vectors. So let me kind of draw this here for a second. We have something like this. I'm just going to put, say, a couple vectors here. Well, I'm going to put 3. Now, when we say there's a subspace, what we're meaning is that there's a certain area, you can think of it, in terms of that overall vector space that can be expressed as linear combinations of the generating set. That's what this is saying right here. So some subspaces of vectors are going to actually be pretty important for defining the overall space. So subspaces are going to be important. Now let's see how this works. To understand it, we need to define the concept of linear independence. Okay, linear independence and dependence. Okay, so we're going to say that a set of vectors, here's one vector, here's another one, depending on how many we have in the set. We could have, say, 2, we could have 3, we could have all the way up to k. We call a set of vectors linearly independent if no vector in the set can be expressed as a linear combination of other vectors. So what does this mean? Okay, this is the matrix algebra definition of linear independence. Now I'm going to make this really conceptual here, because if you just learn the matrix algebra definition, you're never really going to kind of get the big idea as to what this is about. So I'm going to have a vector here of, say, 0, 2, and say 5. There's a vector. It's got 3 elements to it, 0, 2, and 5. I'm going to put another vector here, and I'm going to say this is 1, 5, and 13. Here's the idea of linear independence and how we're going to relate it to information. Is this particular vector providing different information than this one? Okay, that's the question. Is this vector providing different information than this one? If it is, then they're linearly independent. They're linearly independent because they're providing different information. Now, in this particular case, we can kind of see that one vector is not a scalar multiple of another vector. So it's kind of obvious in this case that this vector is telling us different stuff than this one. But if I do this, 2, 3, and 4 as one vector, and then I do another vector here as an example. Okay, you look at this scenario and compare it to this one. You see the difference, right? You can kind of see it right away. You say, you know what? Yeah, you have 2 vectors here, but is this vector really providing new information? Not really. And you can see it, right? You can say, well, this vector here is actually just a multiple of this one. So if I take a scalar 2 times this vector, so multiply each element, I'm going to get 4, 6, and 8. So this second vector is kind of redundant, right? Information-wise, think of it in terms of information. This vector here is kind of redundant. How many vectors do I really need here to describe the space, to describe what I'm talking about? Probably just one, right? That's the idea. You don't really need two, you just need one, right? It's kind of like, you can think of it like almost like twin vectors. Like it's like this one's not telling us any more information. It's just a scalar multiple of this one. Whereas in this particular case, you can kind of see, no, this is telling us something new. So here, the space, the vector space that we're really dealing with is just a single dimension, really, right? When you think of it, because, you know, like one vector is just providing the same stuff. Yeah, it's a scalar multiple, but it's still the same information. Whereas here, you've got a 2D space because you have linear independence over here. Okay. So can you express the vectors as linear combinations of other vectors? Well, if you can't, if no vector in the set can be expressed as a linear combination of the other vectors, then you've got the linear independence. If you can, like we have here, it doesn't have to be a scalar multiple. It can be different linear combinations. Then you have dependency. So if I just go here for a second, there's, say, one vector, here's another vector, here's another vector. You know, maybe 2 times vector 1 is equal to 3 times vector 2 plus 1 times vector 3. That's a linear combination, right? This vector could be explained or accounted for by that particular combination. So it doesn't have to be an exact scalar multiple, but I'm going to tell you right now the easiest way is to think of it in terms of the scalar multiple with 2 vectors. It gets a little more complicated when you have more than 2, but think of it like this in terms of the duplication of information to start to get your head around this idea. Otherwise, you have dependency. So what does this mean? Don't worry about the coordinates with respect to basis. Don't worry about any of that. Here's what it all means over here. Okay, this Fox summarizes this really, really well. Just going to see if I can't bring that down just a little bit. Maybe here so I can see all of it at once. So here we have a subspace, right? We have a vector subspace, and here we multiplied the vector by a scalar. Okay, we multiplied the vector by a scalar. Well, we're still in 1D. That's what that's saying, is one-dimensional space over here. Simply because we elongated the vector or shortened it, we're still in a 1D subspace, right? Well, look over here. We have a 1D subspace as well. Now, why do we have a 1D, one dimension, subspace here? Well, here we only have the one vector. We just multiplied that vector by a scalar to lengthen it, or you can shorten it. Still 1D. Look at this situation. We have 2 vectors, one vector here and one vector here. One vector is on top of the other one. Okay? One vector is on top of the other one. That's an example of dependency. How much information is being communicated here? We don't need both vectors. We really just need one of them. Therefore, the subspace, right? The subspace here is really still in 1D because of this dependency, okay? Because of this collinearity. Now, the idea of collinearity isn't exactly the same as in multiple regression, but kind of the principle is similar, isn't it, right? When we were in multiple regression and you had x1 and you had x2, and you said, hey, those are collinear. What was the decision? How did we deal with that? So there's your dependent variables equal to x1, x2. What was one way of dealing? Well, you can compute VIF statistics and all that, or you can just say what? You say, you know what? Drop x2. Get rid of it. Just keep x1. Why? Because, you know, the correlation here is 0.98. Now, whether I ask your age in months or days, wow, those are actually going to be almost the same. It actually probably should be about the same. So let's just get rid of one of them and just keep one of them, because we have a dependency. Information is being duplicated. Information is being duplicated here, so we're still in 1D space. It's like, you're not kidding anybody by having x1 and x2. The Venn diagrams are like this. It's even worse. That was a bad diagram, but they're even worse, right? So you're still in 1D. That's what's going on here. Now let's look at this particular situation here. Notice that we have two vectors, x1, x2, the same number here. Only that in this particular case, x1 is here and x2 is here. In this particular case, for C, these are, as Fox says, two linearly independent vectors generating a two-dimensional subspace, which is called a plane instead of a line. One dimension is a line, two is a plane. Two linearly independent vectors generating, you notice the word, right? Generating a two-dimensional subspace. They generate the two-dimensional subspace. These two vectors here, x1 and x2, do not generate a two-dimensional subspace. But you say, yeah, but there's two vectors. Yeah, but they're generating a 1D space because of that collinearity. In this particular case, they're generating the two space, the two-dimensional space. So what does this mean? Generating the two-dimensional space means like this in terms of the information idea we're talking about. It means, you know what? You need these two vectors to describe the space. You need x1 and you need x2 to describe the space. They generate the space. Whereas here, you don't really need the two vectors to talk about the 1D space because of that collinearity. Over here, this is an interesting case here. So these three kind of make sense, right, in terms of what's going on. Look at part D, three linearly dependent vectors, two of which are linearly independent. Okay, so two of these vectors are linearly independent. Don't know which ones they are, but because you only have two linearly independent vectors, you've got a 2D space situation here because you're generating a two-dimensional space. So again, this idea of how many vectors, this is the central question. How many vectors do you actually need to generate the particular space that you want to work in? Do you really need all these vectors? Or can you, say, get away with fewer vectors to generate the space? Because if you have a lot of vectors, you could still be, I mean, if I put, what, x3 on top of this, and x4, there's x3 and there's x4, what space am I in? I'm still in 1D space because of the collinearity. So the question is, do the vectors you have generate that n-dimensional space? Or is there duplicates going on? Hope that's kind of clear. And we're gonna see, as we proceed in multivariate, we're gonna see that it's a lot about this generating the space, right? How many vectors do you need and what's going on? And again, if you liken that to the collinearity issue in multiple regression, it gets you started. It doesn't get you all the way there, but it kind of gets you started there. So say, how many variables do you really need to make the prediction? Do you need all two? Do you need three? Let's think of it in terms of stepwise, even though stepwise is not the best regression, but you know, if I have x1 to x10, what do we say? Well, you have, say, 10 predictors, but how many do you really need? Well, if x5 and x6 and x7 are like on top of each other, well, maybe you can get rid of them. You actually need two to generate things, right? To account for variability, to account for information, you only need two. Okay, some stuff on cosines here if you want to take a look, not really essential. We talk about orthogonality of vectors, x and y. We're talking about perpendicular vectors at a right angle. Their inner product is equal to 0. So there's one vector, there's another vector. We know how to compute the inner product. If that inner product is equal to 0, then we say that those vectors are orthogonal. So we're going to be, looking at things like this, orthogonal, the original coordinate system, those axes x1 and x2 are orthogonal. If we do a transformation on this, what if I move this coordinate system? This coordinate system is actually quite arbitrary the way it is, right? It's kind of sitting into space, right? We could have put that anywhere, right? Like there's no reason why it has to be exactly like that. It could be like this. There's the right angle, 90-degree angle. The orthogonality is preserved even though the coordinates have shifted a little bit, right? So what we're going to call this later in the course is we're going to do a rotation. We're going to rotate things, but we're going to maintain the angle, okay? And that's used in factor analysis a lot. More stuff here, not too essential. Talk about the matrix rank is pretty important. Okay, what's the matrix rank? Well, the way to think about the matrix rank is we talked about linear independence. Okay, linear independence, so that kind of providing separate information. Well, when we talk about the rank of a matrix, we're talking about how many linearly independent columns are there and how many linearly independent rows are there. So we call that the dimension of its row space. So the dimension here is if I have my vectors right here, this is information, if these are all linearly independent of one another, so I have a linearly independent set, then the rank is equal to 3. If these two are basically scalar multiples of one another, let's say, but this one is separate, right? Well, then I have only that rank of, that would be a rank of 2, okay? So the rank is how many linearly independent columns or rows do you have in the matrix? Okay. That's either 2 or it's 1. I forget the formality on that. That could be a rank of 1 or 2. But you get the idea in terms of that number of vectors that are providing independent information, and we're going to describe it as the rank. More stuff here, more algorithm ideas on how to get rank and stuff like that. The computer is going to provide us with the rank, right? When we talk about a full rank matrix, just to do another diagram. When you say this is a full rank matrix, well, it's got 2 linearly independent columns and it's got linearly independent rows. The rank of the columns is equal to the rank of the rows. And that's kind of like one of the fascinating things about linear algebra is the column rank is equal to the row rank. Let's get to eigenvalues and eigenvectors, and then we're actually going to be pretty much done what we want to look at in terms of these linear algebra notes. This is a really important topic, but we need to develop further concepts in order to have any kind of feel for what it's doing. But let's kind of try to develop some intuition behind it. And it starts off with what we talked about earlier, AX equals lambda x. Okay. You start out with this equation and you move things over. So you go AX minus lambda x is equal to 0, and then you pull out the A and the lambda, you throw in the identity matrix here, and you have the x here, and you'll get this equation. But it all starts with this, okay? Fox, unfortunately, doesn't put this equation first. It would have been nice if you put this equation first and show you get this. So he kind of starts kind of in the middle of it, which what I'd like to focus on is this equation here. I'm just going to redraw it. AX equals lambda X. What is this equality actually communicating? Well, this is a vector, and this is a vector. Okay. So we have the same vector. This is a matrix. A is a matrix, and this is a scalar. So it's a number. So when you look at this equality, let's ask the question, what is this equality actually saying? Let's put it into words. It's saying that if you take a vector, X is a vector, and you multiply it by A, because implied here is multiplication, A times X. You multiply it by A, by some matrix, like a covariance matrix, like a correlation matrix, or even any matrix in its full generality and abstractness. That could be basically any matrix for which you can multiply by X, so long as it's conformable. You take that matrix and multiply it by X. When you take that matrix times X, that's equal to the original vector, but multiplied by a scalar. Okay. So what is going on? What's going on is saying, instead of having all of this stuff in A, which is a matrix, you can actually just use a number. You can use a number to scale, multiply the vector by. So instead of all this, you can use this. This number here is going to be called, oh, I'm just right here. Where is it? An eigenvalue. And this vector, X, is going to be called an eigenvector or a characteristic vector or a latent vector. Okay. Now the word latent, now that might ring a bell, because you think, hey, that's kind of like what we read a little bit in Boland. Right? We're looking at those structural equation models and things like that, latency. Right? And that's how this is going to be used in psychometrics, is you're going to be computing these vectors, and they're going to be called latent vectors. Now, there's nothing latent about it here. It's here. Right? You have a vector, you have a vector, you have the eigenvalue, you have a matrix. There's nothing latent. Think about what latent means, right? It's kind of like, it's not really here. It's kind of under the Lyman somehow, but it's here. There's nothing latent about it. But when you add a little bit of substantive kind of juice to this, you're going to get the latent idea. So there's a latent vector. Now, that's going to be, you can see where that's going, because if you think of this latency idea that's discussed in Boland, you're talking about kind of like the factor analysis idea, like the construct idea, right? Like, we don't really have the observed variable, but there's a latent variable. So, the distinction between latent variables and observed variables is kind of fuzzy, but you can see that this is where some of this is going to be used to describe that stuff. That's why it's called latent vector. Otherwise, it's not latent in the equation. Now, where some of this stuff started off historically is trying to see, what are these hidden things that kind of, you can think of it in terms of governing a system, right? And it was actually applied with the Earth, called like the axis of rotation issue. Is there an axis or kind of a coordinate system for which the Earth is doing its movement? And is there some kind of underlying theme or underlying structure for which we can't visually see? There's the latency idea. Characteristic vector, another one, or just eigenvector. Eigenvector actually means, it's a German word for characteristic vector idea. But there's the fundamental equation right here. And we do some things with that so we can solve this. And what we do is we find the roots of the equation. So not necessary to look over this right now, but that's what John Fox is doing here. He's finding the eigenvectors and the eigenvalues of the matrix. So he finds like eigenvalues here, and then he finds eigenvectors, And that's what we're going to be doing when we get to principal components analysis. What this really is, when we solve for this equation and we operate on it, we're actually doing basically a version of principal components analysis. And what we're going to see is we're going to take a transformation, and there's going to be some vectors that are special, which are going to be called these eigenvectors. Those eigenvectors are not going in our transformation. So here we have, say, a whole bunch of vectors. I know this is an incorrect dimensional space, but that's okay for the example. Imagine we have a whole bunch of vectors here. I'm going to issue a transformation on all this. So I'm going to go T transform. Well, all of these vectors will get pushed off their span. So this thing here, right here, will get pushed off. So instead of being here, it's going to go like this or something like that. They're going to like kind of go all over with the transformation. Almost think of the transformation like you're squeezing a fruit. Okay, there's the original fruit. You're going to squeeze the fruit. Everything gets misshaped. Everything gets pushed off. Right? All these vectors get moved around. But this vector here, that doesn't get moved around. So you look in the fruit, imagine you could open the fruit and say, my goodness, there's a vector in there that's not being moved. It's actually not being knocked off its span. It's not being knocked off its position. It's actually staying there. Everything else is moving, like the fruit's moving, right? Like the peach is like just squish, squish, except for this one. That one there is an eigenvector. That's an eigenvector. So you see it's a characteristic vector of the transformation. It's not a characteristic vector by itself. It's a characteristic vector by the transformation. That's the eigenvector. Now this eigenvector will undergo some change. Usually what's going to happen to the eigenvector is it either shrinks or it gets longer. So here it is before the transformation. And here it is after the transformation. It got elongated. So due to this transformation, it had the effect of not only locating where that eigenvector is, but transforming it. By how much? How much did it lengthen it by? By a scalar multiple. What's the scalar? The eigenvalue. The eigenvalue, which is just a number, is going to scale that eigenvector. So take a vector x, issue a transformation on it. You're going to have a characteristic vector, eigenvector, that isn't getting moved around. It's a special vector, but it's just being transformed. As we're going to see later when we survey the methodology, we're going to see that these eigenvectors, and there could be many of them depending on the dimension of the matrix, but these eigenvectors are going to be the weighting load elements of the principal component. So they're going to be the actual coefficients to the principal component. Okay, and we're going to see that later as we go. So again, if this doesn't make much sense, it's extremely abstract. You'll see how these things are used later and how to kind of associate with eigenvalues and eigenvectors in a kind of substantive context. And that substantive context is still going to be rather abstract, but then we're going to apply it to real data. Then we're going to say, okay, hey, you got 1,000 variables. Let's pull out some eigenvalues and eigenvectors to consolidate the matrix and get the primary amount of information from it. So you don't have to read through this stuff. You have to just get what we just looked at. Here's more properties of eigenvectors and matrices. Again, yeah, they're there for completeness. Positive definite matrices, not necessary now. We might talk about them a little bit as we go. And that's pretty much it for the matrix algebra. So we've covered kind of the main components. And again, at this point, you know, everything before this is really like a full year of taking each of these topics and unpacking them slowly. And we're covering it in a very, very short amount of time. And the thing is that's all we really need to do. We don't need to spend 2 months doing this. We can actually just kind of look at this appendix, and as we go on, return to it. So as we go on with the course, and I say, hey, look, that inverse, remember the inverse, and I'll refresh us on what those things mean. And you're kind of using the appendix as a catalog. You're not memorizing any of this stuff. You're not even kind of fully understanding all of it. You're kind of just getting the feel for it, right? Like, get a feel for those vectors, get a feel for the inverse, get a feel for that. And then the more you see it, the more you kind of go, okay, yeah, that makes sense. And you have some of that foundation of linear algebra under your belt, which is important, because otherwise you'll never really know what's going on in the multivariate procedure if you don't know what these like dimensional spaces are and stuff like that. Next week, we will talk about calculus. So there's next week, our second full like math preparation idea. And calculus is important too, because so many things in statistics are determined by calculus. So we'll do the introduction of calculus, maybe review a little bit of that linear and matrix algebra, and then we'll be into the Introduction to Statistical Learning book, and we'll be off and running. So again, you can wait and see what I cover of the calculus stuff. I would work on the problems, the homework problems, refer to the linear and matrix algebra as needed, but I wouldn't, like, in terms of a study strategy, I wouldn't be like going through line by line of this stuff trying to make sense of it. I would just kind of go through what we talked about and maybe just refresh on that. In the next assignment, the write-up that will be given out next week, there'll be a few elements from here of what to do with these matrices and stuff like that. But again, computing these things isn't really going to be worth it that much, because it doesn't provide very much insight. It's more going to be what's the kind of substantive idea behind it. Okay, so that's it for today, and we'll see you next week.